In our discussion about the properties of Z transform, we have seen the differentiation property and convolution property. Now, convolution property, just now we stated that when we convolve the two signals in the time domain, actually what happens in the Z domain, in the frequency domain, that it gets multiplied. That is, their Z transforms gets multiplied. So convolution in time domain is multiplication in frequency domain, and multiplication in frequency domain is multiplication in time domain is convolution in frequency domain. So that is a vice versa. So this is a universal property. You have to remember it like this. Okay. So convolution of the two signals. So we use the formula for convolution here for the two signals. We are just revising what we have done already in the last lecture. Okay. So we have used this formula for convolution here. Okay, then we use this substitution z raised to k into z raised to minus k is equal to 1. Okay, then we separated out these two summation equations. Okay, in this equation one summation is missing here. Okay, so when you write this, rewrite this, include the summation for k also in this equation. Okay, so here, then after doing this substitution, okay, we get these two separate equations. So one equation is for this and one equation is for this. So this we can write it as x1 of z, and this we can write it as x2 of z. Hence we can see that the convolution of the two signals in the time domain, the Z transform of the convolution is nothing but multiplication of their Z transforms. Okay, this is your Z transform. Okay, so see here, this just the variables we are using different variables. So here the variable is k, here the variable is p, here your variable is n. So that doesn't matter what variable you are using. Fundamental equation of Z transform you should know in order to understand what is the Z transform. Okay, so Z transform equation you should know. Variables can change. Okay, next in this equation, okay, now let us try to understand. See this here, one more thing, we have to make a change here. Instead of here n equal to minus infinity to infinity, it should actually be k equal to minus infinity to infinity. Okay, because this here the variable is k here actually. Okay, so let us see one numerical. Like we are given two signals here, x of n and h of n, and we are asked to find out what will be the Z transform of the convolution of these two sequences. Okay, now we have to find out the Z transform of the convolution of these two sequences, or simply the question may also be like this, like if these two sequences are given and you have to find out the convolution of these two sequences without using the normal time domain convolution. Okay, we have studied how to find out the convolution of two sequences in the time domain in the section 1. We had seen like how we can make use of the matrix method, we can make use of the graphical method, tabular method for solving the convolution. But here we are not doing the first section. We are asked to find out the convolution in the Z transform using the Z transform. So how to find out the convolution using the Z transform? So we can use the property of Z transform of convolution property. It states that the convolution of the two signals in the time domain is nothing but is simply their multiplication in the Z domain. Okay, so what we can do is simply find out the Z transform of x of n. Let us call it as x of z. Let us find out the Z transform of h of n. Let us call it as h of z. Simply multiply these two things, x of z and h of z. You will get what we call it as the Z transform of these two signals, convolution of these two signals. Okay, so my first task is I will write the Z transform of this x of n. So x of n is a causal sequence. So the Z transform is simply here, which I have written 3 minus 2 into z raised to minus 1 plus 2 into z raised to minus 2. So how to get this convolution we have already seen by solving the numericals on Z transform. Similarly, I have to find out the Z transform of h of n. Okay, so my convolution, my Z transform of h of n is like this. Similarly, I have got this again from the same formula. Okay, now I have to find out the Z transform of the convolution of these two signals. So I make use of the property of convolution. It is nothing but the multiplication of this. So I just multiply these two functions. So I open the brackets and multiply everything here. Okay, so after multiplying, rearranging the terms, adding and subtraction, what I get this equation. So now this equation is nothing but in the Z domain. Okay, I have to get the time domain sequence, which is the convolution in the time domain. So how to get the time domain sequence from this Z domain? So simply you have to take the coefficient. So this is 3, so this coefficient is 1, then this is again 3, so this is 3, this is 3. Your z raised to minus 5 is 0. Okay, so minus 5 term is missing, so it is 0, and this is the sixth term. Okay, so this is your signal in the time domain 3 1 3 3 3 0 2. So if you compute the convolution by matrix method also, by solving this two signals convolution, you will also get the same answer here. Okay, so this is how we can simplify the numerical of convolution by using the Z transform. So Z transform property of convolution is a very important property. So just there is no need of doing the convolution of the two signals in the in the time domain. Simply you have to take their transforms, multiply the transforms, and take the inverse of the transform. You will get the convolution. Okay, so in this way we can make use of the convolution property in order to solve the numerical of the Z transforms. Okay, convolution property of Z transform is useful for solving the numericals on convolution. So summarizing all the properties, we can see that we have seen so far, we have seen the linearity property. Here only the equations are mentioned here. Proof we have already seen. We have seen the time shifting property, what happens to the time shifted signals. Okay, if it is minus k, it will be minus k. If it is plus k, this will be plus k. What is the scaling in the Z domain property? Okay, so it is simply a raised to minus 1 z. So a raised to n x of n is nothing but a raised to minus 1 z. So remember this equation. This is the important equation. Time reversal equation. If you do the time reversal in the time domain, it leads to reciprocal in the Z domain. So x of z becomes x of z raised to minus 1. Then differentiation property. If you take the derivative of x of z, okay, it will lead to multiplication with n. So n into x of n is equal to minus z into derivative of x of z. Convolution property, it states that the convolution, if you take the convolution of two sequences in the time domain, it is simply the multiplication of the two sequences, multiplication of their Z transforms. Okay, now one more property that is important is the called as the initial value theorem. What is this initial value theorem? Initial value theorem is used to find out the initial value of the sequence. Like if by using the Z transform, I can find out what is the initial value of a sequence. Now what does it say that? Now if x of n is a causal sequence, by causal sequence we mean that x of n is equal to 0 for negative values of n. Okay, so the first value of x of n, that is x of 0. So 0th index value x of 0 is simply the limit of this Z transform with Z tending to infinity. So this is an important formula. By using this formula, we can find out the initial value. Hence it is called as the initial value theorem. We can find out the initial value of the time domain signal, that is x of 0, by using this theorem. So it is called as the initial value theorem, provided that we should know the Z transform. Okay, so the proof of this is very simple. Since x of n is causal, I can write the Z transform like this. I have changed the limit from minus infinity to infinity to simply 0 to infinity because it is a causal sequence. Then if I expand this equation, I get this. Now what will happen to this equation if I put this z tending to infinity? So if z is tending to infinity, so infinity raised to minus n will all become 0. So all the terms beyond this x of 0, this will become 0 0 0 0 and so on. So simply I can write here limit of x of z with z tending to infinity is simply x of 0. So this is what is called as the initial value theorem. See, understand the mathematics here. When z is tending to infinity, so infinity raised to minus 1 is nothing but 1 upon infinity, and 1 upon infinity is 0. Similarly, infinity raised to minus 2, 1 upon infinity square, that is infinity. So 1 upon infinity is 0. Okay, so all these terms, these all terms will become 0, and only you will get this term. Okay, so that's why we are writing here limit of x of z with z tending to infinity is x of 0. So initial value theorem is also an important property which we can use to find out we can use to simplify the numericals on Z transform. So in this way, whatever the properties are there in the syllabus, we have covered those properties for the Z transform, and the numericals based on those properties are important. To understand the properties well, we should know an example of that numerical. So whenever you study any property, study the numerical on that property so that your understanding becomes clear about that property. Okay, with this we end with the topic of the properties of Z transform. Okay, in the next lectures we will talk about inverse Z transform. Thank you.